is called critical state. Critical state means the soil has reached a state where you can apply under the same stress, it continues to deform. So you gain strain without no further increase in stress, which means it's same as in plasticity, you reach the plastic limit and you therefore deform without any further increase in stress. So from this, what we can learn is soil is highly nonlinear, and also if I unload it, it's not going to come back. So if I unload from here, it will probably come here. If I unload from here, it will probably here. It never comes back to zero. As I said, we talked about earlier. Okay, so this is, you probably have this data as part of your lab even. Now suppose I want to model this soil. Typically in civil engineering, what do? You can scale down models, right? So, and build a nth scale model, maybe 1 in 100 or 1 in 50 scale model, and you'll test the model. For example, I don't know, what would you have done? I don't know if you've done any bridge engineering or something. Say you want to model the flow of a river in hydraulics. What you don't hydraulics lab, where they would have scaled all the critical values are the same. Normally, like the Reynolds number, Rayleigh number, hydraulics is full of these non-dimensional numbers. So you make sure that the model and the real prototype have the same Reynolds number, typically. Thank you again. You're an angel. I had bad throat, so I'm struggling through the lectures today. Anyhow, so that works for hydraulics. People do something similar in structures as well. You can scale down models and build them and test them in wind tunnels and stuff if you want to look at the vibrations of bridges. In soil mechanics, we got a problem because if you scale everything down, our stress and strain are going to be small model is very high. It's almost vertical. So the stiffness is small model is very high. It's almost vertical. So the stiffness is very high. And you say, right, I built a model, say I built an earth dam, and I want to predict how much the model settles. I can measure it. And then I want to use that to predict what, when I build the big dam, how much that one is going to settle. So if I use this, I get say 2 millimeters of settlement. It's the 50 scale model. I'd predict that my actual prototype is 50 times more. So I'll get 100 millimeters of settlement. That would be your prediction if it's all linear. But because this is all non-linear, the actual stiffness you get will be this and that, right, for dense and loose sands, which are a lot smaller than this. So when you end up actually constructing the dam, you'll see that the dam in the field has settled maybe 300 millimeters or 400 millimeters. And you say, whoa, that means something has gone wrong. So we know this already. This is why we don't build small scale models in geotech and try to predict what the big thing will do. So what can we do to fix this? So you understand the problem. Anybody not sure what I'm talking about? So we know what is going to go wrong here, right? So we can't do small scale models. However, if I can get the stress and the strain in the model same as in the big field structure, prototype structure, then I'm in business, right? So we need to find a way to create the same stress and same strain as in the real structure without actually building the real one. Of course, you can always build the real structure and find out how much it settles. But by that point, it's a bit too late, right? Because you spent all the money, went and built the structure, the thing settled or even collapsed, and then you lost all the money. So that's not how engineering should work. You must be able to predict beforehand what it'll do. So basically, centrifuge modeling is a way of doing exactly that. And the principle of centrifuge modeling is so easy to understand. It literally can be done on the back of an envelope. So let's assume that we got a cube, a rectangular block with dimensions L, B, and H. And let's assume that the mass is M. And it's under normal gravity, 1g. So if I asked you to work out what is the pressure this block is going to apply on the ground, what will you say? M times G is the weight, and the area that is sitting on is LB. So my vertical stress simply should be mg over LB. Easy, right? Exactly same way, if I want to define strain, some change in length over original length is how you define strain, right? So alpha is some characteristic length, and therefore epsilon is change in alpha, delta alpha over alpha. Now just imagine that I have another block which is scaled down by a factor of n. So the length is now L over n, breadth is B over n, height is H over n. That's all we did. We squashed the block by a factor of n, all dimensions. So I ended up with a smaller block. Because all the dimensions are n times smaller, the mass of this must be this big mass over n cubed. Agreed? Because all the dimensions are a factor of n smaller. Now, just for a minute, let's imagine that we're going to put this block in a gravity where gravity is n times bigger. G is your acceleration due to gravity, but for this block, we somehow will make it sit in n times the normal Earth's gravity. If you can do that, let's calculate what the pressure this block is going to exert. So the mass is m over n cubed, and the gravity here is n times g, over length is L over n, breadth is B over n. And as you can see, all the n's cancel out, and I recover exactly the same stress mg over lb as I had here. So although this block is smaller, because the gravity has been increased, it will also apply exactly the same stress. So the soil below this block and below that block will think that they are exactly being subjected to the same stress. Easy, right? Imagine why we couldn't think of this before the lecture. It's so easy, anybody can think of this. What about strain? Same thing. The change in length will be smaller because the model is smaller, but so is the original length. Again, they are smaller by the same factor, n. So again, you cancel these n's and I recover the same strain. So between the prototype and the model, we get the same stress and same strain. And that is what centrifuge modeling is. So how can we increase the gravity is the only question we have. One option is we can send our model to Jupiter. Jupiter has 32 times Earth's gravity. So we can use the scale factor of 32 and do all the tests on Jupiter. Unfortunately, space travel is very expensive and no civil engineer is going to get funded for that. Let's forget that. We need to find a way of creating high gravity on Earth. But we learned this in your school physics that if I put an object and rotate it with an angular velocity omega, then I'll get a centrifugal acceleration of r omega squared. Anybody who doesn't know this? Otherwise, we have to go back and check your, not the gates, what score do they get? JEE score, is it? If you don't know that, we'll have to go back and check the JEE score again. So this is very straightforward. So all I have to do is to create an object that rotates, and I'll organize the angular velocity omega such that if I want ng should be equal to r omega squared. R is the radius at which I'm going to hold the model and spin. That's it. For example, there is a centrifuge. I'll show the picture in IIT Bombay, which we helped build. And say you want to do a test at 100 times the Earth's gravity. So the left-hand side will be 100 times G. The radius of the centrifuge in Bombay is 4.25 meters, and the omega I can work out. That will come in radians per second. I can convert that into RPM by just multiplying by divide by 2 pi, multiply 60, I'll get RPM, right? So I need to spin the centrifuge at 145 RPM. It's not even that fast. Your washing bin machine runs much faster during the drying cycle. However, the issue is how big these things are. So this is our Cambridge machine, and this one is 10 meters in diameter, and it was designed by a guy called Philip Turner. That's why we call it the Turner beam centrifuge. 3 months ago, it turned 50. We celebrated its 50th birthday, and it's still working. So that is where I started my centrifuge testing career. I was a numerical modeler and up till that point. But there are bigger machines. This is the, you know, centrifuge is the biggest one. This is the U.S. Army waterways in Vicksburg, in horrible, horrible Mississippi. If anybody of you are thinking of going to U.S., I suggest you look at the pictures of mosquitoes in Mississippi. They are close to small elephants, but they fly and bite equally hard. US is not all this dreamland, by the way. So I spent for my sins 3 weeks on this machine when they were constructing it. And again, this is a 700 G ton machine. Most of the centrifuges are classified as G tons. How many tons of soil it can carry and what is the G it can go up to. Our centrifuges can carry 1 ton in Cambridge and can go up to 150 Gs. So that is a 150 G ton machine. This one is a 700 G ton machine. So this can carry a soil of 2 tons to 350 G. The Bombay one is a 200 G ton machine, if my memory serves right. About 3/4 of a ton up to the 200 G, I think. There are other centrifuges. The ones I showed you till now are all in for research in universities. I should have the Bombay one also somewhere. I'll come to it. This one is special because the Japanese decided when my professor Andrew Schofield was trying to make it popular, centrifuge modeling, they used to come to Cambridge even when I was a student, look at everything, take photographs, and they went back and built their own centrifuge. Takanaka is a big construction company. For them to build a centrifuge, they build buildings which are 100 floors high and big bridges. So building a centrifuge is like easy for them. So they built this machine, and they do, for every project, they do centrifuge testing and numerical analysis and submit 2 reports by the time they come to tender. So you can see where construction industry in Japan is compared to where we are. Here you're lucky to get some analysis by the time you go to tender stage. This is the beautiful Bombay machine. It's a very nice picture BVS has given me. Homemade, built in India. It was Atmanirbhar before Atmanirbhar was invented. This was constructed about 25 years ago. And Chandrasekharan wanted to build this all. It's built by a company called Mekong, which I don't think it exists anymore. But it's a quite nice machine and it's quite robust. The reason I'm in India at the moment is we're trying to get an earthquake actuator for this. And with a little bit of luck, by January, we should be able to do earthquakes on this. We'll see. There are other type of centrifuges as well. Like we have a mini drum centrifuge where instead of having just one model, you can make the model all the way around, just like your washing machine. You put clothes everywhere, not just in one end, right? It actually balances it better. And for some problems, this is quite good way of doing this. And that's the sand pourer we designed in Cambridge. Okay, where are we in the world? Centrifuge modeling, when I started, every time we had to say, every conference, every seminar I gave, people will say, yeah, it all sounds good, but can it do that or can it do this? And we don't believe it and all that kind of stuff. But now I think after 30 odd years, I wrote a book on this centrifuge modeling for civil engineers. If you're interested, maybe your library has a copy. And it's now accepted as a reliable way to investigate complex geotechnical problems. There are over 85 centrifuge centers around the world, South Korea, China, everywhere. In India, we only have one, but there are several IITs and other places trying to get more centrifuges. One of the nice things about this area is every 4 years, like World Cup cricket or World Cup football, depending on what's your taste, we have a conference and we all go and meet at some nice location. The last one was in Daejeon in South Korea. And the nice thing about this community is, if I develop something, I'll go and present at that conference and everybody else can copy that, imitate that. We don't mind. So we don't compete on hoarding technology, we share the technology. And where we compete is in bidding for projects. That is different. We are developing, these are all just tools. In the end, you should make your money by your brain. So what is the new thing I modeled, or what is the problem I'm trying to solve? So it's not about technology, it's about the problem. We also have a journal now, it's called International ICPMG, and you can publish papers there. So it's kind of established, is what I'm trying to say. Right. This is a slightly esoteric slide. And it comes from my PhD thesis for some 30 odd years ago. What I studied was a tower structure on liquefiable soil with a raft foundation, and I wanted to see what the rocking behavior of this is. So several floors high and so on. Now I talked about scaling this down, right? This is the actual full-size field structure. Use scaling laws to reduce the size. So this is the exact 1/nth replica of that. Now this one will be maybe 30 meters high, and this one will be maybe that high, right? Once you scale it by a factor of 100. Now in this sized model, I can't create windows, doors, the beam column joint stiffness correctly and so on. Yeah, it'll be difficult. I can't actually scale all the structural components exactly right. So what we don't do that. What we do is, you got to think here, what is it I'm trying to model? What I'm trying to model is the rocking of this. When the earthquake comes, this whole thing shakes and rocks. So I need this building to the same as that. But if I simplify that to a cantilever beam with a lumped mass on the top, then I should be able to capture the rocking and the sliding behavior correctly. So instead of spending time making intricate models like children, we simply construct this. This one will have the same flexural stiffness as the big building and has the mass at the right location, and that's all I need. One extra step we got to do is to go from here to here. What this is if this is the centrifuge model I ended up with, I should scale this up and see what it looks like. Yeah. So if I scale this up, it looks like this. Then I look this and this and see what did I lose. Okay. And this is very important, because If I started with an elephant, did all this, and came here and it became a monkey, then you can't say monkey and elephant are the same, right? So at least the elephant should have four legs, big mass on the top, trunk in the front, center of gravity at the right place. It should look similar. It may not have the same shape, but it certainly should look similar. If the species is changing and it suddenly grown a very long tail, like a monkey, then something has gone wrong and you got to go back and do the model design again. So when we say prototype, we generally mean this. That is the full scale field structure. This is the prototype. Right. Now, we are not doing this scaling thing just for fun. What we want to do is to link what we can see in the model during an experiment and predict what the real structure will do. That is the aim of the whole exercise, right? So we need some rules or laws that link the behavior observed in the model to the field structure. So these are called scaling laws. But we already know several of these. I'll list them in a table. We already derived stress and strain. It should be the same in the model and prototype, right? So that is one. Length means that we'll squash the thing by n. So 1 over n. Area is 1 over n squared. Volume 1 over n cubed. Mass 1 over n cubed. Acceleration n times larger. This we already know. So I just put them in a table. So these are the simple scaling laws. Now, what about things we haven't considered? For example, force. And this is very interesting because often in geotechnical engineering, you want to test piles. And pile testing is quite expensive. Especially if you want to apply a lateral load on pile, the whole thing costs, I don't know, maybe 20 lakhs. Because you need to have a reaction frame, push the load, apply the load to the pile, see how much it deforms, measure the displacement, measure the force. In the field, it costs a lot of money. But let's see whether we can do it better in a centrifuge. For that, I need a scaling law for force. But what do we know about force? Force is mass times acceleration, right? So force is mass times acceleration. So 1g and the acceleration as a. In the model, the mass is m over n cubed, acceleration is n times bigger than g, right? So if I want the ratio between the force of the model and prototype, I divide one with the other, I'll get 1 over n squared. This is quite in our favor. Why? Let's see. Suppose I need to apply something like 200-ton load onto the pile cap. Now 200 tons is like 2 meganewtons in SI units. If I'm doing a test at 100G, then the force I need to apply in the model is 2 times 10 to the power of 6 newtons, mega is 10 to the power of 6, divided by 100 square. I only need to apply 200 newtons or about 20 kilogram force. So suddenly I can apply these loads using little actuators in the centrifuge, and I'm modeling something that is very much bigger. So we can do a lot more testing like this and determine pile load tests easily. There's something even nicer. I believe you learned a little bit about consolidation, and consolidation of clays is one, I can say, the bane of geotechnical engineering, but that's where we make most of our money too. Because people want to put embankment buildings on clay. They want to know how much it's going to settle 10 years, 20 years time from now. And we say, we'll pull out the pen and paper, do the calculations and say, this is our best guess. But very often the embankments settle more than what you calculated 10 years. That's why even the road that are being constructed now, they settle a lot more in 5 years than you expected, creating potholes and whatnot. However, The theory for consolidation is quite mathematical, very easy. When you put a load, if the pore pressure increases, you call it U. So dou U by dou T is the rate change or time change of the pore pressure. You link that using a coefficient of consolidation to second derivative spatially of U in X, Y, and Z directions. Great. And we can solve this PDE until cows come home. But that's not how geotechnical people work. Basically, you work out what is called a time factor. You again should know all these things. And that you will say is CVT over D square, where CV is the coefficient of consolidation, D is the drainage distance, distance to the nearest drainage path, T is the time it takes to get consolidation. Basically, TV tells you to get 90% consolidation, how much will the T be? If I want 95% consolidation, what is the TV factor? And you can work out the time for that. Obviously, these things take a long time, right? Now we want to model the same thing in the centrifuge. So I wrote the same equation at the top for prototype and here for the model. Now, what I want is the left-hand side of both should be the same, because the model must have the same degree of consolidation as I would want in the field. Yeah, so TV should be, the time factor should be the same. Also, if I use the same soil as in the field in my model in the centrifuge, CV should be the same, right? That is just it depends on K and E naught. So K and MV, I guess we call it E naught. Anyhow, that is the same. Then the only things that are time and the distance for drainage. So we did that. So if I now get the ratio between time for model and prototype, that will become D model over D prototype squared. Again, the model is 1 over n times of that of the prototype. So my time for consolidation also scales as 1 over n squared. Right? Now let's have a go. Suppose I got marine clay, 10 meter thick, of the Mumbai offshore, and let's say it takes about 10 years to reach 95% consolidation. It's not far off truth. Now, I want to do the same test on the Bombay marine clay in the centrifuge at 100 G. Then I'll say, right, 10 years, 365 days, 24 hours, 60 minutes, 60 seconds, divided by 100 square. Yeah, just substituted the numbers. Nothing fancy. Then, if you work the numbers, that turns out at about 9 hours, 8.8 hours. So, what I just did means that I can predict what the Bombay marine clay is going to do in 10 years' time by running my centrifuge for about 9 hours. Now, this is what is the definition of time machine, isn't it? You are telling what's going to happen in 10 years' time now. That is your time machine, or closest in geotechnical engineering, you're going to come to time machine. So, it's great. So, for problems that are diffusion based, this works great. For problems where you need to apply force or energy, it all works in our favor. Similarly, seepage flow, we can do this. You can use the Darcy's law and show that the seepage flow actually is n times larger in the model compared to the prototype. This is where you need to be careful. I included this because it doesn't work in our favor. The seepage velocity in the model is n times larger than the actual seepage flow velocity in the field, which means that you must make sure that the actual velocity in the model is small enough that you get this small enough Reynolds number. So you make sure the Reynolds number is the same in the prototype and in the field. They won't be exactly the same value, but both will be in laminar range rather than turbulent range. So we can get around that. There are some limits on centrifuge testing as well. We've got about 10 minutes, I believe. 10 minutes, right? Yeah. So some of the limitations are how far can you push this? And let me give you an example. Suppose you want to model a pile. The pile I want to model, for argument's sake, is half a meter in diameter, 500 millimeter standard concrete pile. Now I want to model this in the centrifuge. I can do it at 100 G. Then the diameter of the pile will be 5 millimeters. Suppose I do it at 200 G, it will be 2.5 millimeters. What we're saying is by increasing the G, I can basically put a knitting needle into the ground and call it pile. That doesn't feel right, does it? Somehow pile needs to be a bit bigger. And you're quite right in thinking that, because if I have a needle, the number of particles that are in contact with the needle will be maybe 2 or 3 soil particles. Whereas a real 500 millimeter diameter pile will have thousands of particles in contact around it. Now, both are not the same because I can move individual grains easily. So, this thin pile won't do the same as the large pile, although you got the right stress. So, that's because we made the G so high, we are starting to violate the principles of continuum mechanics. So, the funny thing about soil mechanics is we all know that our particles are individual particles, but all our theories come from continuum mechanics. We somehow, for the 50 years till now, we managed to bridge across that and say theories developed for continuum mechanics can be applicable for soil because we measure gross properties. And it's the same here. You just need to make sure that your pile is of reasonable size and you've got enough particles in contact. So don't do this test at 150 G, do it at 50 G. Then you got 20 millimeter diameter pile and then you got enough particles in contact. And there's a guy called Tatsuoka who came up with shear band theory and counted how many particles are needed to form the shear band. And he said at least 15, 20 particles must be there. So as long as the ratio between the pile and the number of particles is about 15, you'll be okay, or greater than 15. So I've done all that. I don't want to do that. You can basically match for geoenvironmental problems as well. There's one thing I wanted to do, which is modeling of models. Now, there are situations where it's not possible for us to derive scaling laws as easily as I've shown you. For force, consolidation time, we could derive them easily. But there are problems in the world where, for example, cracks are forming in the ground and you want to get there, or ground or ice even, and you want to capture that properly. But for this, the scaling laws are not known. In fact, the slides I skipped, there were two professors in Cambridge. One was my professor, Andrew Schofield, and the other one was called Andrew Palmer, who's a solid mechanics professor. They were both interested in cracking of ice because of Arctic ice and melting and hitting installations in St. John's in Canada. And the professor in solid mechanics said the scaling law should be n to the power of 1.5, and my professor said it should be to the power of n to the power of 1. And they're both big professors, and we couldn't quite argue who is right and who is wrong. But luckily, centrifuge testing allows you to a way of verifying the scaling laws itself. Okay, and that is called modeling of models. To demonstrate this, what I've chosen here is an embankment 5 meters high, sitting on soft clay 4 meters thick, and bedrock below. Okay, that is the prototype problem we're looking at. We can quite easily do 2 tests. So that is my prototype, and I can scale this at 75 G or 100G. If I do it 100G, the embankment is 50 millimeters high, 40 millimeters of soft clay. And if I do it 75G, this is 67 and 53. So I can do both tests, right? Now, if I do this, oh, by the way, let me ask you a quick question. Which of these model embankments do you think will settle more and which will settle less? Just as a guess. Come on. This is at 75G, that is at 100G. Which one will settle more? You got to speak up. I'm a bit deaf. 100G one will settle more. Right. Everybody makes the same mistake. This settlement here would have the scaling law for settlement will be, it's a length dimension, will have a factor of n, right? Because it's the same as the length of the thing. Settlement has the same dimension of meters. So if I have settlement, say this has a settlement of 2 millimeters, the prototype will have settlement of 2 times 100, 200 millimeters. Agreed? So this 75G1, if my scaling law is right, should settle more so that when I multiply the settlement number by 75, I'll get the same 200 millimeters, right? So this one will show you more settlement. Agreed? So it's kind of fun to do this. If you actually do the test and both gave the numbers, when you scale up, they match, then you know the scaling law for length is right. So we can go do this kind of thing for each of the parameters or any unknown scaling factor and derive the scaling factor using the centrifuge itself by doing tests at different G's. And this is what is called modeling of models. Okay? And that is another nice thing to know. I think. Yeah. So here are some numbers. So 100G, 3 millimeters will give you 300 millimeters, whereas the 75G one will give you more settlement, 4 millimeters, multiplied by 75 to give you the same 300. There is another fun thing as well. It's not the ultimate settlement only. The rate of settlement is also going to be different. Can you think about a little bit? This is going to hurt your brains a bit when you think about it. So normally the settlement characteristic for consolidation problem should be something like that, right? It will be an exponential decay curve. Yes? So if that is the prototype, how does this look for 75G and 100G? You think? Because this is time, this is settlement, right? But the 75G one will scale as 1 over 75 squared. I don't know if you can see this or not. Whereas the other one, the time scales as 1 over 100 squared, right? So this is something you probably want to sketch when you go back to your room and see how should this curve look so that when I scale them up, I'll end up with the same thing. So not just the magnitude, the temporal variation or time-based variation also changes. Has to change. There is no question because we know consolidation we already derived the x-axis should scale as 1 over n squared. And if that scale factor is different, I know the final pressure I get to and the initial pressure should be same, but the curve they follow will be different. Yeah? So the rate of consolidation will be quicker for 100G test compared to the 75G test. Okay. I think that's all I wanted to do. Yeah, just to wind up, It's what the advantages of centrifuge modeling are. We create prototype stresses and strains, which means we capture true behavior. No argument there. There's no argument by any professor anywhere in the world. We have now sufficient evidence. Using centrifuge modeling, we can test new materials for which we don't know the stress strain behavior, or we can test the materials under loading regimes which we don't know their behavior under. Example, earthquakes. The biggest advantage of centrifuge modeling is it will always capture the true failure mechanism. The rest of the course, the GYAN course, we are talking about how piles fail in liquefying soils. And the reason I'm so confident to offer a lecture course like that is because I'm confident that when we do these experiments, our centrifuge test will capture the right failure mechanism. And we are having great fun going through buckling of piles and the rest of it this morning. Also, the doing centrifuge tests means you're capturing the true three-dimensional behavior. Even today, you can run 3D finite element analysis, but they take quite a long time and give you a lot of complicated information which we can't understand. But because these are physical models, the true 3D behavior has always been available for centrifuge modelers. Soil structure interaction is automatically captured. So if I have any structure in my soil, the interaction will be automatically captured because it's all physical. Consolidation times are low, forces are small, energy is also small. The reason I didn't put energy is that is one of the reasons why centrifuges were built to start with is to look at blast effects. So close to Operation Sindoor, I didn't want to go into blasts and the rest of it. So let's be civilian and civilized and stop there. But it also can do that very well. Any questions? Either I'm a very good lecturer or you didn't understand a thing. There are only two reasons why there won't be any questions. It's all new for you, right? You haven't seen anything like this before. So it's quite natural that you should have questions. And don't feel shy. I'm not going to bite you. And my teeth are quite old anyhow. Even if I bite, they don't sink in.
I have a question for regarding the pile material stiffness scaling.
Yeah.
How can we do it?
Okay. Easy. Say you're interested in bending of pipe. Yeah. Like what we've been talking. Get rid of this. So in the model and in the prototype, you want the same EI, right? So this is my flexural stiffness. Say you have steel pile, 500, millimeter dia with some wall thickness, 2 millimeters. No, it'll be probably more, 5 millimeters. Yeah, you can work out E steel and I steel pile for that, which is pi by 4 d outer squared, not squared, 4 di, something like that. Yeah. So you know this, you work that out. Now on the model side, say I'm going to make an aluminum pipe. So E aluminum and I of the aluminum pile similar, but my pile let's say is D outer is 20 millimeters and D inner is 16 millimeters. Yeah. So I can work out this and this will be for at model scale. So then I scale this up by factor of 4. to work out what the EI is and make sure that is same as this. That's it. If I do that, my flexural behavior will be matched perfectly.
For flexible rigidity, we have to match.
Match that. Similarly, if you want to match the axial stiffness, you go to do E times A. Look, you can't do centrifuge modeling not knowing mechanics, but these are easy, right? So we can choose the material, choose the section to do that matching. Straightforward. Anything else? Yeah.
If we are doing centrifuge modeling, for let's say account of earthquake, if we're doing this for earthquake, will the what's the relationship of n? If we increase n, does it help?
Very good question. I'm going to do this as part of tomorrow's lecture. If you are very keen, please ask the professor and come and join. Are you an undergrad here? Yeah, come to that lecture. Skip whatever lecture you have at that time and come to my lecture. Yeah, we'll do the dynamic centrifuge modeling separately. That's a totally different beast. I'm on recording, right? Maybe I shouldn't advise students to skip their classes. Anything else? This is all fun stuff. That's why I wanted to do this topic for the combined audience, because there's no complicated maths or anything here. We just went through what we already know. It's just a way of thinking. And I hope you found that interesting. Engineering is like that. Problems can be complex, but solutions and the way we think about it should be simple. That's been my motto all through. I do apologize for my groggy voice, but there you go. You get what you get. Too much Amritsar lassi, I think. Okay, we'll stop there. Thank you.